Hello everyone, this is S.K. Mehta, presently the President of the Indian Nuclear Society called INS, established in 1998. I wish to welcome you all to this INS series lectures. This series about 13 lectures is aimed to acquaint you with the various aspects of the nuclear energy, its utilization in various areas benefiting humanity, the limitations and the regulatory aspects in safety and protection. One of the main objectives of the INS is to promote the advancement of nuclear science and engineering and technology related to the atomic nucleus and the allied sciences and arts. With this objective, INS has been disseminating information through journals, books, reports, newsletters, seminars, and conferences. These have mainly been to keep the INS members and other scientific communities and organizations well informed about the development in the various areas of science and technology within India and world over. Or it is realized that there is a need to keep the various professionals, undergraduate students, and general public knowledgeable in their respective fields of nuclear science and engineering. For the benefit of the public, some of the important and the common application of nuclear being for power, industrial use, medical diagnosis and treatment, agriculture, food preservation, and various other areas. This lecture series is made in simple language and illustration with the aim to inform the general viewer about the science, engineering, and technology, social benefits of the nuclear, application of nuclear carrier benefits in nuclear and regulatory and safety of the nuclear energy. The presentations are prepared and narrated by experts on each topic in a way that the viewers with no background knowledge about the nuclear science and engineering can understand. Our effort will be to constantly provide information about newer benefits to the society emerging out of the painstaking research and nuclear science and engineers. Viewers are encouraged to comment, suggest, and put forward questions to the experts. The channel of the constructive communication will always be open in INS, which is website ins-india.org.
Hello everyone, I am Vipul Shiralkar. I am from Nuclear Power Corporation of India Limited. I am here to deliver a presentation on nuclear reactor safety, which is under INS Lecture Series 2022. So, safety of a nuclear power plant in India is a very important topic, and it is utmost necessary to provide correct information to all the viewers and general public. As such, safety is accorded the highest priority in all activities of a nuclear power plant. All nuclear power plants are sited, designed, constructed, and operated in accordance with strict quality and safety standards. The principle of defense in depth, redundancy, diversity are followed in design of all the systems of a power plant. The concepts of defense in depth, redundancy, and diversity will be introduced in this presentation, and you will get a fair idea and develop a complete understanding about them in this end of this presentation. The regulatory framework in the country is robust, wherein the rules of safety standards, monitoring, and enforcing are well laid down. Safety is ensured by proper design, material selection, controlling zones of radiation, controlling collective exposure, training, then inspection, and monitoring safety drills, and carrying out plant shutdowns, then necessary upgrades also, then review process and strict regulation in proper graded approach. Now let us see the details of nuclear reactor safety through this presentation. In this complete presentation, first we will develop a concept of safety as a foundation, and we will see its applicability for nuclear power plants. This is analogous to learning of a new subject. While learning a new subject, we define some goals, like we have to finish the subject by the end of this semester. For this, we search for some reference books, some textbooks, and some guiding books also, and then we start studying that subject. Similarly, here, for nuclear reactor safety, we set some safety goals. Then, for that, for achieving that safety goals, there are some principles or guidelines for achieving the nuclear safety goals. Now, mind you, these safety goals are set by a very high level authority at international and national level. At international level, it may be International Atomic Energy Agency, and at national level, for India specifically, it is AERB, that is Atomic Energy Regulatory Board of India. Then we will see the safety systems of a nuclear power plant. We'll see ESFs. ESFs are engineered safety features. After that, we will develop a concept of defense in depth. Just have told you about this. Then at the end, we will see the licensing and regulation process by AERB, that is Atomic Energy Regulatory Board. Just like for driving a car on a road, you have to have a license. Without a proper license, you cannot drive a car. So just like for operating a nuclear power plant, you have to have some license, and there are some regulations. Regulatory rules are set by AERB. Before directly addressing the concept of safety for nuclear power plants in the context of nuclear power plants, let's see or let's develop the concept of safety by a simple example or day-to-day example of safe driving of a car. Now I am assuming here that before driving a car, you are having a proper valid license. This is the first level of safety. Okay. Now I have listed down some points which ensures the proper safety of a car while driving. Now also look at the order in which I have listed them down. We will go one by one. First, for having a zero incident or zero accidents, we have to have a good quality car. Then we have to follow the traffic rules set by the transport authorities. Now, for having a freedom from danger or risks that are likely to cause harm, what we usually do, we fasten the seat belt. Fastening of the seat belt ensures that even though some kind of unforeseen events are taking place, we still have risk limited to some lower value. Then we limit the speeds in the range which is set on the highway. Okay. After that, we have some degree of acceptable unsafe condition. What is this unsafe condition? Some kind of I will explain this by an example. There are some chances that we have a damaged rear mirror or improper windscreen wiper. Even though these are somewhat unsafe conditions while driving a car, but based on driver to driver skillfulness, there is some degree of acceptability for these kind of unsafe conditions. Even though these unsafe condition directly does not lead to unsafe driving of a car, but still there is a degree of acceptable unsafe. After that, for identification of hazards and for their management, we have some kind of features just like low fuel tank, low coolant level in radiator. These instruments provide a proper information to the driver about the condition of a car. These are known as hazard identification systems. Then, in case of some accidental loss, what we do, we postulate these accidental losses and we design some systems which are taking care of the driver and uh, other persons present in the car for their safety. We are designing some airbags so that the precious lives of the people sitting in the car are protected. Now, some cars also usually provide some fire extinguishers also to take care of the fires that are ignited in the car. Okay. Safety in nuclear reactors is ensured by many things. I have listed down some major highlights or major points to ponder on. The first and foremost is high quality design and construction. By ensuring high quality during design and during the construction, the first level of safety is itself ensured. How we are achieving this? This is done by having intrinsic design features. We are following safety guides, safety codes which are accepted nationally and internationally. Then we are having a safety culture. This is the generic phrase which is used among the nuclear fraternity. Safety culture is actually a way of life of a nuclear engineer, a nuclear scientist. We are day in and day out, we are thinking about the safety of a nuclear power plant. Then we are having a quality control in place during the design stage, during construction stage, during operation stage, and during our maintenance stage also. Then we are having a testing and inspection program, which is also known as in-service inspection program for nuclear components. Then for then we are having systems in place for detecting operational disturbances or human failures and errors before developing into programs. These standby systems takes necessary actions and have no human intervention also for taking fast actions. So these are very fast acting systems which are in place in the nuclear power plant. Then we are operating with the standby and diverse systems. I will give an example. If there is a requirement of two pumps for operation of a system, then we are having another one pump which is acting as a standby, which is not coming into action directly. If one pump gets shut down, then this other pump will come into action. This is known as standby. The third pump will be on standby. Then we are having diverse systems. What are diverse systems? Diverse systems are the systems which are having the operating principle which are completely different. If one system operates on the principle of electromagnetism, then another system should operate on the principle of photoelectricity. Just like these, we are having a diverse system. We are always operating with the standby and diverse systems to control and to prevent the possibility of radioactivity release. Now we are having comprehensive monitoring and regular testing to detect the equipment or operator failure. Just like we are doing kind of service or doing a maintenance of a car, we are also doing a comprehensive monitoring and regular testing. Regular testing is also known as a preventive maintenance check, PM checks. Engineering students might be knowing about this. We are doing regular testing to detect the equipment or operator failures. Then there are provisions to confine the effect of any damage within the plant itself, within the plant boundary itself. Just like an example of airbags, here also we postulate, even though the possibility of this postulation is very low, it is far low, still we postulate these kind of failures, and for these failures we design a systems which are known as engineered safety systems. We will see them in the upcoming slides. Now, there are some safety goals which are set by International Atomic Energy Agency. This is the apex agency in the which is a part of United Nations organization, and they have defined some safety goals in the form of pyramid. Uh, there are some top level safety goals, some upper level safety goals, then intermediate level safety goals, and at the foundation there are some low level safety goals. The basic philosophy incorporates the topmost priority of a nuclear safety is the protection of society. Then at the upper level and at intermediate level, it ensures the safety of the site. What is meant by site? The site is actually the location at which the nuclear reactors are located, which includes the boundary outside the nuclear reactors also. Now, and at the foundation level, it ensures the safety of the facility. Facility includes the nuclear reactor itself. Then, the International Atomic Energy Agency also describes that safety goals for the society and site should be technologically neutral. Here, I want to add here that There are various types of nuclear technologies, namely pressurized heavy water reactor, pressurized water reactor, boiling water reactors, gas cooled reactor, and there are many other type of reactors. Even though there may be differences in the technology of a nuclear power plant, still the safety still the top level, upper level and intermediate level safety goals which ensures the safety of the society and site shall be maintained and shall be ensured, while the facility level safety is basically technology specific. The safety of a facility is is actually dependent on the type of the reactor technology we are using for. So here we will see what are these levels which are set by IAEA in some further detail. Now as a part of continuation of previous slide, here we will see what are top level, upper level, intermediate level and low level safety goals, and we will define them. In top level safety goal, the IAEA guideline ensures the protection of people and environment from harmful effect of radiation. Now, as a part of this INS lecture series also, we will be getting acquainted with the radiation doses which are received by the people, and you will come to know that the radiation dose received by the public at at the boundary of the power plant is very negligible, very negligible. So this guideline ensures the prevention of harm to public and to the environment. Second level is the upper level. It ensures adequate protection in all operational modes of facilities and installation at the site. Now, when there are various operational states of a power plant. The installation may be operating, installation may be under shutdown, installation may be during startup, installation might be having some kind of maintenance. During these all operational states, there should be an adequate protection. Now, at an intermediate level, the IAEA guideline provides IAEA guideline ensures the general safety based on the proven approaches and good practices to ensure adequate protection. Here, we have some principles of safety margins. Incorporate the principles of safety margins during design, during operation, during maintenance, and during day-to-day activities of a nuclear installation. Similarly, there are some physical barriers to ensure the adequate protection, namely fuel, clad, and coolant. What are these? We will see in subsequent slides. Now, at the foundation level or at a low level, safety goals, the IAEA guideline ensures that it provides specific safety for each facility and installation. As I already told you, depending upon the nuclear technology which we employ, there are some specific guidelines which ensures the safety of the facility and at the end installation. Now, as an example, there is a limit on maximum fuel cladding temperature. We have to maintain this maximum fuel cladding temperature within certain limit based on type of installation we are having. By ensuring this, the safety of a facility is ensured. So by employing all these levels of protection, the overall nuclear safety is basically addressed. Now we will briefly see the operation of pressurized heavy water reactor with the help of this schematic for Indian PHWRs. In India, we are currently having 18 operating pressurized heavy water reactors. In pressurized heavy water reactor, we are using natural uranium as a fuel and D2O, that is heavy water, as a coolant and moderator. Coolant takes care of the cooling of the fuel, and the moderator is present for thermalization of the neutrons. When the sufficient amount of fuel is kept inside these tubes, which are known as coolant channels, continuous chain reaction is started. Whenever the continuous chain reaction is started, tremendous amount of heat by means of nuclear fission reaction is generated. to take care of the amount of neutrons which are generated during this fission chain reaction, and to control this chain reaction we are having the reactivity mechanisms. To take care of the cooling of the fuel which is present inside its coolant channels, we are having PHT, which is known as pressurized heat transport system. By means of a pump, the coolant is pumped through these coolant channels, and the temperature of the coolant increases by coming in a contact with the fuel, and this heat is taken out in the steam generator. At the other side of the steam generator we are having a DM water, that is demineralized water, which in turn gets heated and the steam is generated. This steam is then fed into the turbines, first into the high pressure turbine and then into the low pressure turbine. The steam which then enters into the condenser, and in the condenser it condenses into the water again. This condensate is then pumped back again to the steam generator in the form of feed water system. There is a common shaft for HP turbine, LP turbine and generator. Whenever there is a rotation of the HP turbine and LP turbine, due to the presence of steam flowing through them, there will be a generation of electricity, and this electricity is then fed into the grid by means of these electric lines. Now, to take care of the fuel which is present inside the channel and to take it out and refuel it again, we are having a special machines which are in the form of robots. These machines are known as fueling machines, and they take care of the daily refueling activity. As moderator takes care of the thermalization or slowing down of the neutrons, now this whole coolant channels, reactivity mechanisms are actually present inside a vessel which is known as Calandria vessel. This is a typical feature of pressurized heavy water reactor, and hence pressurized heavy water is known as tube type reactor. Now the whole building which includes the main nuclear reactor is enclosed inside a primary containment, and which is also enclosed in a secondary containment. The primary containment is made up of pre-stressed cement concrete and the secondary containment is made up of reinforced cement concrete. This double containment structure is required for confinement of radioactivity within the reactor building. So this is the basic schematic of a pressurized heavy water reactor. Now there are some fundamental safety functions that has to be followed during nuclear reactor safety. First is the ability to shut down the reactor and maintain it under the shutdown. That which means we have to stop the nuclear fission reaction whenever it is required. In the nuclear fraternity, we term it as a first C. What is C? C means control. We have to control the nuclear reaction, and whenever we require the reactor be shut down, we can shut down. This is a typical animation which will illustrate shutdown of a nuclear fission reaction actually means. Whenever there is an insertion of absorber rods which absorb the neutrons are inserted into the reactor core, then the neutrons available for the fission reaction are get absorbed by these absorber rods, and which controls the nuclear fission reaction or which stops the nuclear fission reaction. Hence, the nuclear reactor is termed as to be in shutdown condition. Now, the second fundamental safety function is the ability to keep the core in cooled condition. Here, we term it as a second C. What is second C? It is cooling. Now, nuclear fuel is some kind of typical fuel where even though the reaction is stopped, still have some amount of thermal energy. Due to this thermal energy, the nuclear fuel as a whole gets heated up. So we have to cool this fuel continuously till its heat is removed. So we have to ensure the core cooling. So this is second C. Okay, it shows the fuel getting cooled by means of a coolant. Okay, and the third fundamental safety function is to ability to contain the radioactive fission products within within a confinement or within a containment. So we term it as a third C, and it is known as containment. So here we have a containment like structure which protect the complete core and which is required to contain the radioactive fission product within a confined and protective boundary. So these three fundamental safety functions now we have understood. Now after understanding the fundamental safety functions, we will see the systems which are provided to meet the fundamental safety functions. These systems are known as safety systems. For the fundamental safety functions which are control, then cooling and then the containment, we are having three different type of systems. First is known as reactor protection or shutdown system, which is intended for controlling the reactivity. Second is emergency core cooling system, which is dedicated for cooling of the reactor. And last, we are having containment systems, which takes care of confinement of radioactive. We will see an examples of all these systems. First, we will see the reactor protection and shutdown system. In a typical 540 megawatt pressurized heavy water reactor, we are having two shutdown systems. First is known as shutdown system 1 and another is known as shutdown system 2. Now we will see the second safety systems, which is emergency core cooling system. In case of emergency core cooling system, we are ensuring continuous supply of water through the coolant channels of the reactor so that the cooling of the fuel even after the shutdown is maintained. The system which takes care of this cooling is known as emergency core cooling system. Now we will also see the third system, which is known as containment system, which takes care of third fundamental safety function. For containment system, let's assume that there is some heated source present inside the core, and if there is a uh, water sump at the bottom, and if we spray some kind of water into that heated so onto that heated source, then the water which is coming in the form of bubbles will take out the heat due to its surface area. Hence, the overall pressure inside the containment will get reduced. This will take care of the confinement of radioactivity inside this reactor building itself. In addition to this containment spray system, we are also having containment filtered venting system. We are also having a provision to vent the air present inside the containment to pass through CFVS, that is containment filtered venting system tank, so that whatever air which is coming from the containment will pass through this system, and the final outlet of this system will be a clean gas. So these are basically the three safety systems. Now, as discussed in our earlier safety of a car example, we are having some systems. We postulate some kind of failure which is having very less probability, and for that also we are designing some systems. In nuclear reactors also we have designed some systems which are known as engineered safety features. Here also we postulate an incident which is having a negligible probability, but still for that also we have designed some safety systems. In our day-to-day life also we are encountering with engineered safety features. Let's see first one. We are having fire extinguishers and fire hydrants in the offices, hospitals, and commercial complexes. These systems are basically provided to reduce down the fire incidents. The fire incidents are basically the incidents which are having a low probability. But still, for these also, we have designed systems and we are kept them on standby operation. Secondly, we are also having uninterrupted power supply or UPS systems. These are provided to have a continuous electric supply even in case of power cuts. So what we have done? We have assumed there might be a situation of power cuts. In that case also, we should not have a interruption of a electric power supply. So for that, we have designed uninterrupted power supply systems. So basically, these are kind of engineered safety features which you might have seen in your day-to-day life. Similarly, in nuclear reactors also, we are having engineered safety features. Now, let us quickly see the definition of engineered safety features in the context of nuclear reactors. The systems or features specially engineered in a nuclear power plant to mitigate the consequence of accidental condition and help to restore the normalcy are known as engineered safety features. Now, what we are doing actually, we are we are specially engineering systems to mitigate the consequence or to take care of the consequences of accidental conditions. Even though the probability of these is very, very negligible, still we are engineering these and these will ultimately help to restore the normalcy. The examples of these include the containment atmosphere cleanup system, containment depressurization systems, etc. Systems which are taking care of these two functions are containment spray system and containment filtered venting system. While giving the examples of fundamental safety functions also, have, I have mentioned these two systems. Now, in the context of engineered safety features, we will see the containment spray system. We assume some accidental condition which is having a very low probability in turn, but we are assuming it to be happening. So what will happen? There will be a rise in pressure of the containment itself. So to reduce this pressure, we will spray water in the form of mist. So these water bubbles will take out the heat and will reduce the overall pressure and temperature within the containment itself. Now, in addition to this system also, we are having a backup system which is known as containment filtered venting system, where some part of this air is fed into the this tank which is known as containment filtered venting system tank, and it is allowed to pass through the stage 1 which is wet scrubber region, then the gas phase region, and then the final separation unit, and ultimately the clean gas is fed to the outside. So there will be a complete cleanup of the containment atmosphere. These systems are basically engineered safety features for a typical 540 megawatt and 700 megawatt Indian pressurized heavy water reactor. There are some principles or guidelines available for achieving the nuclear safety goals. The first and foremost principle is known as defense in depth approach. You may surprised to know that we are using this defense in depth approach in our daily life also. Let's understand by an example. Assume that there is a rainy season, okay, and you go out with a umbrella in your hand. Assume that you have not wore the raincoat. So there is a high probability that you will get drenched by using the umbrella alone. Now, if you are using a defense in depth approach, what you will do, you will have an umbrella with yourself. Along with that, you will have a raincoat. So the probability of getting drenched will get drastically reduced. So you are having defense in depth in the form of umbrella plus raincoat to avoid getting drenched. Similarly, we are using this defense in depth approach for our nuclear reactor safety. In case of nuclear reactors also, we apply this defense in depth principle for the containment of radioactive material by the series of physical barriers. In earlier example, we are having physical barriers, first being the raincoat and second being the umbrella. Here also we are having physical barriers. This diagram shows what I am just trying to explain. At the center of the reactor, there will be a fuel matrix. This natural uranium fuel is is protected by a physical barrier, which is known as fuel cladding. This Fuel cladding also is covered by the reactor coolant boundary. So here with one layer there will be a protection of other layer to its surrounding. So outside the reactor coolant boundary there will be a presence of containment system. Outside this containment system also we are having the site boundary. This boundary is known as exclusion zone. The population is always present outside this side boundary. So for the protection of a population which is present at a distance, we are having number of physical barriers which are backing to each other to take care of the confinement of radioactive material, and hence this whole concept is known as defense in depth concept. Now after developing the concept of defense in depth approach in our day-to-day life, we will see the applicability of defense in depth approach for a nuclear power plant. Here we are having various levels of defense in depth, namely level 1, 2, 3, 4 and 5. There are specific objectives for these 5 levels, and every objective has essential means for achieving that objective. Okay, let's see one by one the levels of defense in depth which are applicable to nuclear power plant. Now, one thing is to be noted that we are following this defense in depth approach during design, construction of equipments, construction of nuclear power plant, then operation of nuclear power plant, maintenance, and during decommissioning also. Now, in the level 1 of defense in depth, the objective is prevention of abnormal operation and failures. And what we are doing for this, we are ensuring that this objective is made by conservative design and high quality of construction and operation. In the level 2, the objective is the control of abnormal operation and detection of failures. If the level 2 will come into picture when there is some abnormality with the level 1, the system will enter into the level 2. So we are having the barrier for level 1, that is level 2. The objective here is control of abnormal operation and detection of failures. We are achieving this by controlling, limiting and protecting the systems and other surveillance features. The level which is acting as a barrier to this level 2 is level 3, where the primary objective is control of accidents within the design basis. To take care of these accidents uh, within the design basis, we have already postulated some accidents, and for that we have designed some safety features and which are in place. These are known as engineered safety features, and we are having some procedures to be followed during such scenarios. These are known as accidental procedures. So these are first three levels of defense in depth. These all these levels comes under the category of prevention. The level which is coming as a barrier for this level 3 is level 4. Now here the objective is control of severe plant conditions, including prevention of accidental progression and mitigation of consequences of severe accidents. Now, I want to mention here that in our Indian nuclear power plant scenario, which is nearly 50 years old, we have not crossed this level 2 of defense in depth. That shows our robustness. So, in level 4, to take care of these control of severe plant conditions, including prevention of accidental progression and mitigation of consequences of severe accident, we are having complementary measures and accidental management guidelines. Now, the level which is coming as a barrier to level 4 is level 5. Here, the main objective is mitigation of radiological consequences of significant release of radioactive materials. And in this level, we have to mitigate the radiological consequences, and we have to restrict down the release of radioactive materials. We are doing this by off-site emergency response. So you will know that anything which is passing from level 1 to level 2, level 2 to level 3 to level 4, and then ultimately to level 5 will lead into the off-site emergency response. So there is a fair level of robustness is already in place in case of nuclear power plants. Now let us just quickly see how these 5 levels of defense in depth are hierarchically deployed in case of nuclear power plant. And let's see the plant states. Plant states are plant conditions. Now, if the provisions for level 1 of DID are successful, then the fundamental safety functions will be successfully performed. If the provisions for level 1 of DID are not sufficient, then there will be starting of an initiating event. Here, there will be kicking in of safety systems and normal and abnormal operating procedures. This level 1 of DID will be backed up by level 2 of DIDs, and if the provisions for level 2 of DIDs are successful, then the fundamental safety functions will still get performed. If these provisions are not sufficient, then it will give rise to design basis accident. For that, we are having safety systems and ESFs. ESFs are engineered safety features, and as a guidelines or as a procedures, we are having emergency operating procedures that needs to be followed by nuclear operators during such scenarios. The level which is acting as a backup for level 2 of DID is level 3 of DIDs, and if the provisions made for in the level 3 of DID are successful, then also the fundamental safety functions are successfully performed. If these provisions are not sufficient, then it will give rise to design extension conditions or severe accidents. Now, here also there will be kicking in of additional safety systems, and severe accident management guidelines will be utilized by nuclear power plant operators. Now, the level which is acting as a backup to level 3 of DID is level 4 of DID. If the provisions for level 4 of DID are successful, then there will be the limited accidental radioactivity release, and if the provisions are not sufficient, then it will give rise to significant radioactivity release. In this case, there will be utilization of emergency plans. So this will come in the level 4 of defense in depth. Defense in depth level, which is acting as a backup to level 4 of DID, is level 5 of DID, and here there will be mitigation of radiological consequences of radioactivity release. This is the last level of defensive depth. Here we try to reduce the consequence of radioactivity release. So with these 5 levels of defense and depth, overall nuclear safety is actually achieved. Now many of you might be thinking that yes, it is okay to have postulations of the accidental scenarios and to design the systems to take care of those scenarios, but it is technically impossible to postulate the scenarios which are not possible, and to design the systems for that scenarios. These conditions are known as design extension conditions. Now the basic fundamental safety functions in nuclear industry is control, that is controlling of the reactivity, then cooling of the fuel, and third is containment of the radioactivity. So basic accidental management approach will also ensure that these three fundamental safety functions are always taken care. So to take care of the first thing, that is controlling of the reactivity, what we will do, we will insert neutron poisons into the moderator so that the controlling of the reactivity will get ensured. Then for cooling of the fuel, we will supply the water. So we are having provisions to inject the water. So the second fundamental safety function will get ensured. The third function, that is controlling of the reactivity within this containment, we are having containment filtered venting system. Also, in case of accident, there will be generation of hydrogen within this containment structure. So to take care of this hydrogen, we have also installed the hydrogen management devices. So in this way, we are doing accidental management. As we have already discussed during the example of a safe driving of a car, we have seen that one cannot drive a car safely on a road even if it does not have a proper license. Similarly, in case of nuclear reactor, we require a license. That license is issued by Atomic Energy Regulatory Board in India. Atomic Energy Regulatory Board, or AERB, is a competent authority for granting renewal, withdrawal, and revocation of consent for nuclear and radiation facilities across India. So this is the apex body which provides the license and provides the regulation for nuclear and radiation facilities across India. The consenting process for a nuclear power plant includes the consent for siting, that is deciding the site. Then it is followed by consent for construction of a nuclear power plant. This will be followed by consent for commissioning. After the construction is completed, all the equipment which are present in the power plant will be operated and it is ensured that they are running properly. After that, after commissioning, there will be a consenting process for operation of a nuclear power plant. Then at the end of the life of a nuclear power plant, there will be consenting process for decommissioning. So let us first see the consenting process followed for siting of a nuclear power plant. Now, while deciding the site where the nuclear power plant to be constructed, the only the sites with very low seismic activity are chosen. No sites in the seismic zone 5, that is most active zone, will be selected. Then in the zone 1 is the least active and zone 5 is the most active. All the sites are located within the zone 1 to zone 4. The environmental clearance from state pollution control board and state environment ministry will be taken. It is ensured that there will be no effect on flora and fauna. Then if the site is present near the coastal region, then coastal regulation zone clearance is also obtained. It is also ensured that there is no effect on aquatic and marine life. There is a special requirement of exclusion zone. This exclusion zone is maintained around in every nuclear power plant. The figure shows seismic zones for various sites of a nuclear power plant. So you can see here that all of our nuclear power plant sites are located within zone 2 to zone 4 regions only. Now after obtaining the consent for siting of a nuclear power plant, the second consent which is required is construction consent. The construction consent is given in one stage or in three substages. This includes the review of overall design safety, including the plant layout, plant building structures, reactor systems, electrical and instrumentation systems, waste disposal systems and common systems. The consent is given in stages for excavation. Then the consent will be given to first pour of concrete, that is first time pouring of concrete for the construction. Then the consent will be given to major equipment erections. Now to give you the feel of how major equipments are erected, I have photograph which I will show here. The figure shows the photograph during the construction of Kakrapar Atomic Power Plant 3 and 4 in Kakrapar, Gujarat. This photograph shows the erection of dome. So this is one of the major equipment erections. Similarly, the figure shows the lowering of end shield or the erection of end shield. Now, after obtaining the consent for siting, the construction will be started, and once the construction is completed, there will be requirement of commissioning consent. The commissioning of all plant systems is done before the actual operation of the reactor. The commissioning consent is given in phase-wise manner before every important step. It is given before hot conditioning, or then it is given before first time fuel loading. The figure here shows the loading of the fresh fuel in the reactor core. It is inserted into the coolant channel. Then the consent will again given before low power physics experiments. Now up to the consent of siting, construction and commissioning, the nuclear power plant is termed to be a project. After the power plant starts operating, it will be known as a station. The consenting process of nuclear power plant during its project stage, that is during siting, construction and commissioning phase, there is three-tier review within Atomic Energy Regulatory Board for granting the consent. So the utility here in India, it is Nuclear Power Corporation of India Limited, that is NPCIL. It will submit its application for site consent to Site Evaluation Committee, that is SEC. Site Evaluation Committee will review its application, and then based on its recommendation, it will submit its report to ACPSR. This is the very high level committee for the project stage in Atomic Energy Regulatory Board. Once the ACPSR clears the proposal for siting, then it will submit its recommendation to AARB, and finally AARB will issue siting consent to the utility. Then for the construction and commissioning phase, the application for construction and commissioning consent will be given by utility to PDSC and CESC. These committees will review the application, and based on their review, they will submit the report to ACPSR. Once ACPSR clears the application, it will submit its recommendation to ARB, and finally ARB will issue construction consent and then the commissioning consent to the utility. Now, when a project turns into the station, that is, when it is under operation, there will be a requirement of operation consent. Now we will see the process followed during granting of operation consent for a nuclear power. So from the first criticality, that is first time start of sustained nuclear reaction to the reactor operation up to 100% of full power, the consent in stages is given by NPC SRC. Once NPC SRC clears the application will be forwarded to PDSC. Once the PDSC clears the application will be submitted to ACPSR. Now, this process will be followed uh, till the reactor achieves 100% of full power for the first time. Now, with the start of commercial operation of the reactor, the continuous full power operation consent is granted from time to time by NPC SRC operation. Then it will be reviewed and approved by station safety committees, and finally it will be approved by SARCO. So ACPSR is the top level committee for project stage, and SARCOP is the top level committee for operating plants. Now, the operation consent needs to be renewed time to time. Periodic safety reviews are carried out for renewal of license of operation for all the nuclear power plants. Now, at the end of life of nuclear power plant, the consent for decommissioning is sought from ARB, and it will be given as and when required. Now, NPCIL, that is Nuclear Power Corporation of India Limited, has the prime responsibility of design, construction, commissioning, operation and decommissioning of nuclear power plants in India. Now this chart shows the performance of Indian nuclear power plants. Can be seen that many of our reactors have operated for more than a year continuously for nearly 38 times, and 7 times we have operated for more than 600 days continuously. So this shows the strong base load power plant role which is being performed by Indian nuclear power plants. Recently, in Kaiga 1, we have set a new benchmark of continuous operation of 962 days. At that time, it has set the world record for continuous operation. Now, along with the capacity factors, there is an excellent track record of continuous safe operation of nuclear power plants in India. Tarapur 1 and 2 reactors have recently completed 50 years of safe operation. We have not seen a single event, even of small quantity of uncontrolled radioactivity release till date in any of the Indian PHWR. This highlights the robust design, our quality assurance, our inherent safety culture among nuclear fraternity of India. So let us summarize the overall presentation. The ultimate objective of nuclear safety is protection of individuals, society and the environment. The fundamental safety functions are ensured by multiple safety systems which are in place. The defense in depth approach is governing principle followed in nuclear reactor safety, and the licensing and regulation in Indian nuclear power plant context is done by Atomic Energy Regulatory Board. Now at the end, I would like to show my gratitude towards the coveted Indian Nuclear Society for giving me this opportunity to deliver this lecture on nuclear reactor safety. For any queries, you can contact me on my email.